we can use that same idea of the net change in order to find absolute extrema when we're given a graph of a derivative. So here we're given the graph of f prime. We're also given the f of 0 is equal to 3. We want to find the absolute maximum value of f over the interval from -6 to 6. So remember, when we see absolute maximum value, I should be thinking about EVT, extreme value theorem. So in that case, we look at two places, critical points and endpoints, to determine where we have absolute maxes and mins. So my critical points are where my derivative is equal to 0 or is undefined. I know my derivative is defined because I can see it on the graph. So that's going to be -4, -2, 2, and 5. Those are all critical points. -4, -2, 2, and 5. My endpoints are -6 and 6. That was given here. And so what I need to do is find f at those values. These are the same places where we would have relative maxes and mins, but we're going to have to do more work to figure out absolute maxes and mins. So we are going to make a table of values. I'm going to split it into two tables. Just so we have enough space. So we have to check -6, -4, -2, 2, 5, and 6. Before we do that, let's go ahead and actually split up our graph so that we can find the areas. It will help us find the integrals more easily. So here we have a triangle. The base is 2, the height is 2, so half 2 times 2 is 2. I have another triangle here from -4 to -2. My base is 2, my height is 1, so that triangle has an area of 1. Here I have a semicircle. So remember, semicircle is 1/2 pi times my radius. My radius is 2. Make sure you're using the radius and not the diameter, squared. So that's half of 4 pi, which is 2 pi. I'm going to go ahead and just label each half as pi just in case I need it. And then I have another triangle from 2 to 5, a base of 4, a height of 2. So that gives me an area of 4. Or sorry, I apologize, I am having trouble counting. My base is 3, my height is 2, so that gives me an area of 3. And this last little baby triangle there, base of 1, height of 1, so that is 0.5 or 1/2. Okay, so I'm going to go ahead and calculate these now. So remember, if I want to find f of -6, what I'm going to do is use my starting value. This is my start value, f of 0, which is 3, plus my integral from my starting value 0 to -6 f prime of x dx. This is my graph of f prime. So if I'm integrating f prime from 0 to -6, that means I'm going backwards from 0 to -6. When I'm going backwards, I do the opposite sign of my area. So I'm going to have 3, I'm going to subtract pi. Sorry, I'm going to add pi because it was negative. So I'm going to add it on, subtract 1, and add 2. So I do the opposite sign if I'm going backwards. That gives me 4 plus pi. At -4, same idea. I'm going to do 3 plus my integral from 0 to -4, f prime of x dx. So I'm going to do 3 plus pi minus 1. I'm only going back to -4, so that's 2 plus pi. For -2, I'm going to do 3 plus my integral from 0 to -2, f prime of x dx. So 3 plus pi. 3 just plus pi going back to -2. Now I'm going to jump over to x equals 2. So I'm going to have 3 plus my integral from 0 to 2, f prime of x dx. So that's 3 plus. My area from 0 to 2, though, is -pi. So that's actually, I'm going to erase that and put a minus. Maybe. Minus pi. All right. At 5, I would have 3 plus my integral from 0 to 5, f prime of x dx. So 3 minus pi plus 3, that's 6 minus pi. And at 6, I'm going to have 3 plus my integral from 0 to 6, f prime of x dx. So 3 minus pi plus 3 minus 0.5 gives me 5.5 minus pi. Now, once we've made that table of values, we're not actually done yet. It did ask us for the absolute maximum value. So we're looking to see which of these numbers is the biggest. Now, you don't need to actually calculate what they are. You can leave them in terms of pi. But 4 plus pi is 7 something. That's definitely bigger than 2 plus pi or 3 plus pi. Got to be bigger than 3 minus pi. 6 minus pi, 6 minus 3 something is definitely big or smaller than 4 or 7 something. 4 plus pi is 7 something. 5.5 minus pi would also be smaller than that. So this value right here is my maximum value. Make sure that you're putting maximum value means the y value, so I don't want to say my maximum value is negative 6. My maximum value is 4 plus pi, and it happens at x equals negative 6. But my maximum value is 4 plus pi. So once again, just make sure we're using the point that we were given, f of 0, and then we're looking at the net change in area between 0 and those other critical points that we were looking at. So the last thing we'll talk about in this section is an extension of that first part of the fundamental theorem of calculus. So when we take the derivative of an integral, essentially the derivative and the integral cancel each other out. But one thing I want you to pay attention to is this change in variables. So here there's an x, but here there's a t. And so what I'm doing is taking the x and replacing the t. Wherever there was a t, I'm going to replace it with an x. So then my function is f of x. So notice the dt goes away. Essentially, I'm taking the derivative of the integral, and I just get f of x. So whatever is inside, just with an x, just a change of variables. We have the same idea here, our second part of this rule, except that sometimes we'll have a function other than just an x. So there might be something else. So I'm still going to take that part and plug it in for where my t is. So wherever there was a t, there will now be whatever my function u was. But I also have to pay attention to the second part. Essentially, we're doing chain rule here. So I'm plugging in a function into my other function. So I'm going to have to multiply by the derivative of the inside. You could use that same rule here, but the derivative of x is just 1, which is why we usually ignore it. So in example 5, we have the derivative of the integral from 0 to x of t squared plus 1 dt. The derivative of the integral, all I'm going to do is take the x, plug it in for the t. So I see the t here, t squared plus 1. All I'm going to do is replace the t with an x. This is just x squared plus 1. So remember, this is just going back to saying, like, if g is this integral, then g prime is just that function inside. All we're doing is changing the variable. In b, we're taking the derivative of the integral from 2 to x of 5t minus 3 dt. So I see I just have one t here, 5t minus 3, and my x, an x, so I'm just going to replace the t with that x, and so I just get 5x minus 3. Again, just a change of variables. So this does get a little trickier if we have something besides x, and so let's look back up at our formula and try to get all this in there. All we have to do, we're going to replace our t with whatever that function is, and then we'll multiply by the derivative of that. So in 6a, what I'm looking for a variable on my integral, and so I see I have this 5x squared there. I identify my t as right there. So I'm going to replace my t with the 5x squared plus 1. But then I need to multiply that whole thing, so let's keep the parentheses, times the derivative of, not the derivative of the inside, it's just the derivative of whatever my u was, whatever the function was that I plugged in, so times 10x. Now I'm just going to leave this factored right now. It's up to you. You could distribute if you want, but usually we like to keep things in factored form, so I'm going to leave that alone. Okay, in part B, we're taking the derivative of the integral from 2 to 2x cubed of 3t squared plus 1 dt. So I've got my 2x cubed, and I see my t here, 3t squared plus 1. So my derivative of my integral will be the quantity 3 times, now that t is squared, so I have to take 2x cubed and square it. So wherever the t was, I'm replacing it with 2x cubed plus 1. That was my integrand, that's this part right here, my integrand. And then don't forget, I have to multiply now by the derivative, not of the inside, but the derivative of 2x cubed, which is 6x squared. I'm going to simplify this just a little bit. 2x cubed squared is 4x to the 6th. So I would have 12x to the 6th plus 1 times 6x squared. In part C, I noticed that this kind of seems backwards from what we're used to. I noticed the variables on the bottom instead of on the top. And all we would need to do is switch the order there. And remember that if we switch the order, then our answer will be negative. So you don't actually have to rewrite the whole thing. You just have to make sure your answer will be negative compared, or the opposite sign of whatever your original function was. Okay, here my t is just up here inside this cosine. So my derivative of my integral will be e to the cosine of x squared. I'm going to multiply it by 2x, the derivative of x squared. Again, I'm only taking the derivative of x squared. But then don't forget, because the x squared was on the bottom instead of the top of this integral, I'm going to make it negative. So this is negative 2x e to the cosine of x squared. Last one, part D. We're taking the derivative of the integral from negative 2 to 5x to the 5th, 1 over square root of t squared plus 2t. So I see that I have my function up here, 5x to the 5th, that I'm using. My t, pay attention that there's a t in two different places, t squared plus 2t. I have to replace both of those with a 5x to the 5th. So I had something squared plus 2 times something. Both of those somethings are 5x to the 5th. And then don't forget, I need to multiply by the derivative of the 5x to the 5th, which is 25x to the 4th. If I rewrite this, I just have 25x to the 4th over square root. Let's simplify a little bit. 25x to the 10th, I multiply the exponents there, plus 10x to the 5th. For our last example, number 7, we're given the function f of x, which is the integral from negative 2 to x of negative t to the 4th minus 8t cubed plus 20t squared dt. We want to determine all the x values for which f has a relative minimum. So that means, just remember this, f prime is changing from negative to positive. I'm not given f prime, I'm given f. So the first thing I need to do is find f prime of x. So remember the rule we just talked about? When I take the derivative of an integral, essentially I'm going to take the variable that's on my integral, which is x, and I'm going to replace wherever there's a t with that variable. And then I'll multiply by the derivative of that x, but that derivative of x is just 1, so I can kind of ignore it. So my f prime of x is negative x to the 4th minus 8x cubed plus 20x squared. At this point, this is just an old type of problem. Really, the only thing new here is taking the derivative of this integral. So we're trying to see where f prime changes from negative to positive. I have my f prime now, so I'm going to find my critical points. So see where this is 0, make a sign chart, and then do my analysis. I can factor out a negative x squared. So I have negative x squared times x squared plus 8x minus 20. Keep track of your signs there. Factor a little bit more, negative x squared times, this would be x plus 10 times x minus 2. That equals 0 at x equals 0, negative 10, and 2. So I can make my sign chart now. Negative 10, 0, and 2. So I could plug in negative 11, that would be negative here, negative, and negative. which would overall be negative. Here I could plug in -1. This negative x squared, pay attention, this is always going to be negative. So that first one will always be negative. This would be positive and then negative, so overall positive. Once you have that first sign, you can really just use the multiplicities here. My signs will change at x plus 10 and x minus 2, but not at negative x squared. So this will still be positive. This one will be negative. So if I'm looking for, again, a relative minimum, so f prime changes from negative to positive, I see that right here. But remember, I have to write out my analysis here. I can't just use my sign chart. So f has a relative min at x equals -10. Since our justification there, f prime changes from negative to positive.